Hello, I welcome you all in this course on steam and gas power systems. Today we will solve one numerical based on vapor power cycle. This numerical is based on regenerative steam cycle, and the statement of the numerical is in a regenerative steam cycle employing two closed feed water heaters. Feed water heaters are used for feeding or are used for heating the water which goes to the boiler, and that is known as feed water. So, heaters, the steam is supplied to the turbine at 40 bar pressure. So, steam at the inlet of the turbine is 40 bar, temperature is 500 degree centigrade temperature, condenser pressure is 0.035 bar, approximately it is exactly 3.5 kilopascal. The intermediate bleeding pressure are 10 bar and 1.1 bar. Find the amount of steam bled at each stage, output of plant per kg of steam and the efficiency of cycle. Now, here in this case, as I stated earlier, the feed water heating is done with the help of steam. This can be done in two ways. One is we pass the feed water through the casing of the steam turbine, but that process is not very practical process. So, instead of that, the steam is trapped from the steam turbine at various locations. Suppose there is a steam turbine, steam will be tapped at various locations, and this steam will be used for heating the feed water going to the boiler. So, first of all, we will draw a temperature entropy diagram for the processes, then physically we will draw the schematic diagram, and then we will solve the numerical. Now, this is temperature and entropy. X is equal to 0, and here X is equal to 1. Now, steam is at 40 bar pressure and 500 degree centigrade temperature. If you look at the steam table at 40 bar pressure, this is 40 bar pressure, the saturation temperature is 250.35 degree centigrade. Therefore, the steam is superheated. So, state 1 is superheated steam. This is state 1. Now, after state 1, it is expanded to state 2 in the turbine. Now, during expansion process, the steam is trapped at two locations, and after the expansion, it goes to the condenser, where complete condensation of steam takes place. This is vapor power cycle, and then compression. I will shift this line, otherwise it will create confusion. So, here 3 to 4 process is taking place in a pump, and after the pump it goes to the boiler, and in the boiler superheating of steam vapor takes place. This is a normal Rankine cycle for power generation with the facility of superheating. Now, now here steam is being tapped, because during this process 1 to 2 the expansion of steam is taking place, and steam is tapped at 2 points as stated here, at 10 bar pressure and 1.1 bar pressure. So, at 10 bar pressure steam is tapped, perhaps the steam will remain superheated in this state, okay, and then desuperheating takes place, and then complete condensation of vapor takes place, and this heat is transmitted to the feed water, because the tap steam tapped here is used for heating the feed water, right. So, the state, let us say 6, we get 6 here, and this is state 7, right, and this state, let us say it is 11. So, from 7 to 11 condensation of superheated vapor takes place. This superheated vapor comes from the tapping, and this vapor is used for increasing the temperature of feed water heater. Another tapping takes place this may be superheated, or let us say it is close to the saturation. So, here again the tapping takes place, and again condensation will take place somewhere here. So, this state is 8, and after 8 the steam tapped at 8 may be superheated, or that we will find out while solving the numerical, right. So, this steam is again condensed, and heating from 4 to 5 takes place in second heat exchanger, and okay, and this point is 9, right. So, this is the entire arrangement. I am repeating, there is a Rankine cycle. In Rankine cycle, from the turbine there are 2 tappings, and these tappings are to heat the feed water, because now when the feed water is heated, now the heat required in the boiler will be only H1 minus H6. Earlier, without feed water heating arrangement, the energy required in the boiler was H1 minus H4. So, this much heat is coming from the tapped steam. Suppose the tapped steam is Y1 here and Y2 here. Okay, 1 kg of steam is circulated, Y1 fraction of steam is tapped here, and Y2 fraction of steam is tapped here, right. So, Y1, let us say Y1 is tapped here and Y2 is tapped here, and we will make the cycle like there is a boiler, right, and from boiler the steam is going to the turbine. So, it is state 1, right. Now, after state 1 it is going to state 2, this is state 2. From state 2 it is going to the condenser, it is going to the condenser, and process 2 to 3 is taking place. Now, after process 2 to 3 it is going to the pump, right, and pump 3 to 4, this process takes place 3 to 4 inside a pump. So, after the pump it goes to 2 different heaters, feed water heaters. There are 2 different feed water heaters. As shown here, after the pump it goes to the first feed water heater and then second feed water heater. So, first feed water heater using Y1 fraction of steam, okay, and Y1 fraction of steam is entering at state 7, this is state 7, right, and it is leaving the feed water heater, this is a feed water heater, and this is leaving it at state 11. Steam is getting condensed from state 7 to state 11, right, and steam entering from here is 0.5 and getting heated up to 0.6. They are not getting mixed. There is a indirect heat exchanger. There is a there is no mixing at all. So, 5 to 6. The steam, the water, feed water is only getting heated in a closed reheater. So, I am repeating, the steam tapped at state 7, right, and it is cooled to state 11. This energy is used for heating the feed water from state 5 to state 6. So, state 5 to state 6 the feed water is heated, at state 6 it is going to the boiler. It is going to the boiler, and from 6 to 1 the heating is taking place inside the boiler. Now, in first feed heater, this one Y2, the second heater, steam is again tapped Y2 from here, and this steam is at state 8, right, and after state 8 where it is going? It is reducing to 9, right, and 9, okay. Now, one thing we have to see here, that steam available at this pressure is 10 bar and this is 1.1 bar. Because once the arrangement is clear to you, solving numerical is not a big issue. But in regenerative heating, one has to understand the arrangement of the feed water heater and the energy transfer, right. So, here pressure is 1.1 bar, here pressure is 10 bar. So, what should we do? Now, in this case, expansion devices are provided at both the places. So, this 10 bar pressure is reduced to 1.1 bar, only then we can mix this fluid with this fluid, right. So, expansion takes place, okay, and in this expansion we get state 12 and this also gets expanded and we get state 10. Because students are often confused why this expansion is taking place. This expansion is taking place, otherwise we cannot mix this water with this water. Because after condensation also the enthalpy is quite high, at 11 also the enthalpy is high. This enthalpy can further be used for heating this feed water. So, now they are connected, right, and this is state 12 and all the heat is imparted to this feed water moving in this pipeline and this goes back to the condenser. Now, the condenser is at again state 10. So, pressure at 10 is equal to pressure at 3, because pressure balancing is very important, otherwise there will be reverse flow of the fluid and everything will be in a chaotic state. Now, here in this arrangement, now let us look at the mass flow rate. Y1 has been tapped from here, Y2 has been tapped for here. So, here is remaining only 1 minus Y1 minus Y2, right. The mixture or the condensate which is going from here to here at state 10, it is Y1 plus Y2 and they are mixing in the condenser and then they are getting pumped to the boiler. So, this is the entire arrangement for this problem. Now, we can do the energy balance. Rest of the things are like simple numerical on vapor power cycle. We can start with H1, enthalpy at 1, state 1. Now, we have to find enthalpies at all the states. What is remaining? Finding out enthalpy at all the states and value of Y1 and Y2. That is it. If we have these values, we can always find the value of everything. Find out the steam bled at each stage, output of plant per kg of steam and cycle efficiency. Now, H1 is, it is superheated steam. So, we will have to refer the table for superheated vapor. So, I have taken out the properties of superheated vapor at 10 kilopascal, 10 bar, it is 1000 kilopascal. So, at 1000 kilopascal and 500 degrees centigrade, sorry, it is not 10,000, it is 40 bar, this is 40 bar. So, superheated steam at 40 bar pressure and 500 degrees centigrade, the enthalpy is 3446, it is 3446.0 kilojoules per kg of steam, right. Now, how to find S7? Because we need S7 also. How to find S7? In order to find S7, this process 1 to 7 is isentropic process, right. So, entropy at state 1, how much is the entropy at state 1? At 500 degrees centigrade, the entropy is 7.0922 kilojoules per kg Kelvin. S2 at 10 bar is same, but if you look at the saturation properties at 10 bar pressure, the entropy is only 6.585. It means the vapor at state 7 is superheated, right. So, we will take the vapor as superheated, and in this case at 10 bar we will have to find, we will have to do interpolation between 250 and 300 degrees centigrade, because entropy will lie, this 7.0922 entropy will lie between these two temperatures and between these two enthalpies, right. So, this we have done, and the value of H7 is 3033.85 kilojoules per kg. Right. So, it is lying between these two, right. Similarly, we can find the enthalpy at state 2. In order to find, I will write somewhere here, S2 again is how much? Is equal to S1 is equal to 7.0922 kilojoules per kg Kelvin, right. Now, if we look at the thermophysical properties or properties of steam at 3.5 kilopascal, the entropy is 8.5211. It means entropy of the gas is 8.52, this 8.5211. It means after expansion or at state 2, the vapor is wet, its quality is less than 1, right. And so, S2 is equal to S1, S2 is equal to S1 is equal to SF plus X SFG at 3.5 kilopascal, and this turns out to be, and this will give you the value of X, and X turns out to be 0.824. Values can be taken from here, they are all the values are given in the steam table, and with the help of this X we can find the value of H2, it is HF plus X HFG, and that is going to be equal to 111.82 plus 0.824 into 2437.68 is equal to 2120.47. Now, what is remaining? 8. Similarly, we can find the value of enthalpy at 8. So, we can have enthalpy at state 1, state 7, state 8 and state 2, assuming that the entropy during this process remains constant. Okay. After finding the values, these values, now H8 I have calculated, the H8 is 2591.4 kilojoules per kg, right. So, now we have enthalpies of all the states. This enthalpy we can always take from steam table, right. Now, what is remaining? Now, here in this case we can neglect the pump work, and if you want to find the pump work, then work of the pump is specific volume at 3 multiplied by P4 minus P3 in kilopascal. That will give you pump work in kilowatt, and volume, specific volume at 3 is a specific volume of liquid at 3.5 kilopascal, that is going to be this much, right. Now, what is remaining? Now, remaining is the value of Y1 and Y2. If we have the value of Y1 and Y2, we can find rest of the things, right. So, in order to find Y1 and Y2, we will have to make heat balance here and here in both these two heaters. Heat balance means how much heat is coming to the heater, how much heat is coming to the heater, and how much heat is leaving the heater, or enthalpy of the fluid leaving the heater, enthalpy of the fluid coming to the heater. Now, in order to do that, we will do the energy balance, that is energy of the fluid available here is Y1 H7. Y1 H7 is energy coming from here, right. This is heater 1, this is okay, plus fluid entering H5, enthalpy of 5 is equal to how much? Energy of the fluid leaving the heater, that is H6 plus Y1 H11. Is it clear? Because this you have to understand very clearly, that the energy which is enthalpy which is coming to the heater, enthalpy of sum of the enthalpy of incoming fluid is equal to the sum of the enthalpy of outgoing fluid. So incoming fluid enthalpy is Y1 H7 plus H5, this fluid is coming to the heater, plus is equal to H6, because this 1 minus Y1 minus Y2 plus Y1 plus Y2 will make 1. So the mass of the fluid or mass of the water which is flowing in this pipe is 1 kg per second, right? And Y11 and Y1 and H11. We have all the values, and from this we can find the value of Y1, and Y1 here is 0.147. It means 14.7%. Yes, you may be wondering how I have taken H6, right? Because H6 and H11 are very close to each other. So they are very close to each other, so we have taken the same value. There is not much enthalpy difference practically, right? So Y1 is 0.147. Now energy balance for this heater, another heater which is at low pressure. Now in this heater, again the energy is coming, or enthalpy of incoming fluid from state 12, enthalpy of incoming fluid from state 8, enthalpy of incoming fluid from state 4, and enthalpy of outgoing fluid. So they have to be balanced, and the final equation is going to be Y2H8. This is enthalpy of fluid at 8, we have already calculated. Y2 we do not know, plus Y1 H12. This is Y1 H12. H12 is H11. It is only isothalpic expansion. So H12 is equal to H11 plus H4. H4 is enthalpy at state 4. Enthalpy at state 4. 3 after pumping, we are getting state 4. Okay, is equal to H5 plus Y1 plus Y2 H9. And H9 or H10 both are same, right? Is it clear? Because H5 is also, this I did not show earlier, this is also the outgoing heat, right? Outgoing energy. So now we have done, there are 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, okay, right? So now by V1 is already with us, the rest of the enthalpies are with us, and this gives the value of Y2 as 0.124. So Y1 we are getting 14.147 or 14.7%, and then Y2 is 12.4% here at state 8, right? Now we have all the values. In order to find the heat given to the system or heat transfer in the boiler, that is going to be H1 minus H6, right? And what about the output? Output of the turbine, now we will have to take output in 3 stages. First stage is 1 to 7, where the mass of the steam is 1 kg. Another state is 7 to 8, here mass of the steam is 1, 7 to state 1 minus Y1 822, 1 minus y1 minus y2. So, now if we have to calculate the value of output of the turbine, for calculating output of the turbine, we have to take H1 minus H7 plus 1 minus Y1, H7 minus H8 plus 1 minus Y1 minus Y2, H8 minus H2. This will give us the output of the turbine. Once we have the heat given to the system and output of the heat given in the cycle, net heat given in the cycle and output of the cycle, we can find the efficiency of the cycle. What was to be found here? Find out the steam, the amount of steam bled at each stage we have already calculated. Output of the plant, the output of the plant you do by yourself. I am giving you the answer to this is 1132.87 kilojoules per kg, that is output of the plant. Heat given in the cycle from the boiler is 2683.5 kilojoules per kg, right. Efficiency will be, this is W by Q, and that will turn out to be 0.422 or 42.2%. The rest of the things you can do by yourself and you can match your results or your answers with these answers. That is all for today. Next class we will start with the steam generators.